Hello everyone, in this video I'm going to show you how to simulate a simply supported circular plate in Abaqus. We are going to use a shell method. So we have a circular plate with a radius of 100 millimeter, and the Young modulus is 2.1 times 10 power 5 megapascal, and Poisson ratio is 0.3. The thickness of the plate is 5 millimeter, and we are applying a pressure of 0.07 kilogram per millimeter, which we can transfer this one to Newton per millimeter. Okay, so let's now first, before doing this in Abaqus, look into a hand calculation. So we have a formula for finding a maximum displacement, which happen in the middle of the plate, which comes from this equation. And in this equation we have something called D, which is a flexural rigidity that we can calculate it from the top. So it's a Young modulus thickness divided by 12 times 1 minus Poisson ratio squared. So if you substitute numbers, values, that equals to 24 times 10 power 6, and then we can use this value in the below equation and we can find the displacement as 1.82 millimeter. Also we can have a maximum stress, which formula, we have a formula for that one as well, that if we put the values in, we'll find the maximum stress equals to 333 megapascal. Okay, so now once we found these values, let's do this one in Abaqus to see that if the results are going to be close to our hand calculation. Right, okay, now I'm going to show you how to simulate this scenario in Abaqus. So we start from a part as usual, create a part, and it's going to be 3D deformable shell and planar, and make approximate size 300, and then click on continue. And then I'm gonna draw a circular part here from the middle section. So from here to here, and give a dimension to this one, and that's going to be 100, and cancel this one and click on done. Okay, so next step is to create a property. So we create a material property for this one, and this is going to be still, and for mechanical elasticity elastic, Young modulus we give it as a megapascal form, E5, Poisson ratio 0.3, click on OK. Next step is to create a section, and because this is a shell, so we're going to create from the category, we're going to go to shell, and it's going to be homogeneous. Click on continue, and here we just need to give a shell thickness, which in this case is 5 millimeter, and the material is still, we only have one material, and click on OK. And now we need to assign this to here, so I'm going to assign the section to this one, click on OK. So the most important part here is this shell offset. Obviously selecting a correct section is important as well. When you have a complex job, you might have more than one section, but also shell offset is quite important. So it currently is a mid surface. What does that mean? It means that when I click on OK, half of that 5 millimeter, that means 2.5 is going to go to the right, 2.5 is going to go to the left. So to demonstrate that, I'm going to click on OK. From view, part display option, I'm going to click on render, apply this, and as you can see, this line in the middle, so that's our shell surface. So when I created this render, half of the thickness went to the right, half of them went to the left. And also I can change this font, for instance, from the section manager. So I can edit this one, and I can say I want this to go to the top surface. So as you can see, all the thickness is going to go to the right, or I can say bottom, so all the thickness is going to go to the left. So when you have a complex geometry, then you have to actually think about where are you going to offset your shell. is it going to be the left and right? Sometimes you have to do a trial and error to find the correct offset, but this is very important, so don't ignore this for complex geometry. Always check this one by going to view, part display option, render it, to make sure that the offset is in the correct direction. In this case, it's a very simple geometry, so we don't really have to be worried about this. I'll keep this one as a middle surface. Click on OK, and then I'm gonna go to assembly, add the assembly part, click on OK, and then in the step I'm gonna create a static one. Click on continue. Non-linear is off, increment, make the initial 0.1, minimum 15, and number of the increment, let's make it 1000. We don't really need that many. Click on OK, and the next step is to go to interaction. Again, this is a simple geometry, you don't really need to do anything here. And then the load section. So first I need to fix the edge, so I'll do that by going to the first option, click on this, and I'm gonna pin this one, click on OK, and then I'm gonna apply pressure to the mid surface. So use a pressure, continue, select this one, click on OK, and we have to select the face. So it's a purple one and the brown one, so I'll go for brown, and I'm gonna apply a pressure which was 0.686. I'm just gonna double check that. Yeah, that's correct. So click on OK. So as you can see, we applied the pressure in the middle. For a mesh, because we imported assembly independent, so it's going to go to part, and we can deactivate render. For a shell, apply. So here the mesh is the category is on free. We can also apply a sweep mesh, but it's not really necessary. We can also apply structure mesh by dividing this circular plate to 4 different sections. Then it's possible to apply a structure mesh, but in this scenario I'm happy with this. I'm going to just apply a mesh seed, and let's say maybe 8 is okay. Let's apply this one. Yeah, I mean 8 is a acceptable size. We can assign this one, run a simulation, and if the result is not close to our hand calculation, then we can come back here and play with the mesh a little bit more. But we don't really want to apply a too fine mesh and then just waste the time for solving it. So always start with the acceptable, not too coarse, not too fine, in the middle, and then later modify your mesh. Obviously for a complex geometry you always have to do a mesh study to make sure that your result is not going to change by changing a mesh size. This is very, very important. So create this one. So I'll call this one circular plate 2. Click on continue. Okay, and I'm gonna submit this job. So now I can monitor this, and this is going to be a quick simulation as well. As you can see, the job is already done after 6 increments, so you can see the result. So if I go to plot, and if I go to first displacement, so displacement is 1.81, and what we got in the hand calculation I think was 182, so very close enough. I'm sure that if we play with the mesh a little bit, we might be able to get that one much closer to the hand calculation. So currently 1.82, and the stress value is 333 megapascal. So we can actually check the stress value as well. So if I go to stress, and that's 338. So again, very close to hand calculation. We can actually go back to mesh section to see that if reducing the mesh size will help us to get a more accurate result. So so I'm going to reduce the mesh size. Let's make it 4, and assign a mesh. So as you can see, I have much finer mesh in this section. And then I'm going to go back to here, and I'm going to submit this job again. So the job is done. We can request the results. So a stress value is 339, and the displacement is 1.82. So the displacement is now close to a hand calculation. However, the stress value obviously is going higher because of we reduced the mesh size. So again, this is the values that we found is in an acceptable range, and it's very normal that you're not going to have absolutely exactly same as your hand calculation. So this is very normal. So within 5 to 10% of an error, or the difference between hand calculation and the numerical result, is totally acceptable. So this is the end of this tutorial. I hope you enjoyed this video. I hope to see you in the next video. Thank you so much for watching.